This is part 1 of the video notes for Objective 4B, Systems with Matrices. In this portion of the video notes, we're just going to practice setting up an augmented matrix from a system of equations and writing a system of equations given an augmented matrix. So, for the first example, we want to go over what an augmented matrix is. A matrix is a tool in mathematics used to organize numbers by row and column. So if you think of a system of equations, like we have in our first example, we have 2 rows, each equation representing a row, and we have 3 columns, 1 for the coefficient of x, 1 for the coefficient of y, and 1 for the constant value. Turning this into an augmented matrix is just a matter of taking each coefficient in each row. Generally, when we write an augmented matrix, we use a vertical bar to delineate between the coefficients of the variables and the constant that the equations are equal to. And this is what we're looking for when we create an augmented. Question B on example 1 is also a system of 2 equations, which will give us 2 rows, except that this system has 3 variables. Anytime you're missing a variable, so the second equation is missing a z, you put a placeholder of 0. Keep in mind, a system that has 3 variables but only 2 equations cannot be solved. In order to solve a system of equations, you need an equation for every variable. The last example is a 3x3 system of equations because we have 3 equations and 3 variables. So we're looking at x plus y equals 1, which gives us 1, 1, and a 0 for z, and then 1 for the equals. Then we have x plus 2y minus 3z equals 4, which gives us 1, 2, negative 3, and 4. And finally, we have 3x plus 4z equals negative 6, which gives us 3, 0, 4, and negative 6. Example 2 in the notes is asking us to do the exact opposite of this. So we're going to take a look at an augmented matrix and we're going to try to write the system of equations that this matrix represents. The first matrix is 1, negative 2, 1, 0, 3, and 6. Now remember, each column represents a variable, and the last column represents what the equation is equal to. So if we were to write this as a system, we would write 1x minus 2y is equal to 1, and our second row would be 3y is equal to 6. Example B, or part B of this example, is a 3x3 system, and what you can tell because it's a 3x4 matrix with the 4th column representing the solutions to each equation. So we are looking at turning this back into equations, and we get 1x skip 2z equals 5. Skip y plus z equals 3, and z equals negative 2. Now, this example is what we call row echelon form, or Gaussian elimination. And in this particular form, you can see a few traits that are key to Gaussian elimination. So the first trait I want to draw your attention to are the 1s on the diagonal. The second trait that makes this Gaussian elimination are the 0s underneath. In this type of elimination, we can then solve the system because we have the first variable and we can plug it back into the second equation to get the second variable, which we can then plug into the first equation to get the first variable. We won't be using this specific type of elimination in our class because we're going to be practicing what's called reduced row echelon form. And so reduced row echelon form, we have an example in the notes printout just to highlight the differences. The example in our notes is 1, 0, 0, 0, 1, 0, 0, 0, 1, and 9, 5, negative 2. And so this is called reduced row echelon form, or it's also referred to as, that's not how you spell Gauss, Gauss-Jordan elimination. And in this one, we still have 1s on the diagonal. However, we have 0s both below and above. And so this is the type of elimination we'll be utilizing in our class, because in this format, we get one variable, one answer, one variable, one answer, one variable, and one answer. This concludes part 1 of the video notes, where we just focused on setting up an augmented matrix and writing a system given the augmented matrix. In part 2 of the video notes, we're actually going to complete the row operations and practice the row operations that are necessary to solve a system using an augmented matrix.